Okay, in this fourth and final problem in the vapor power chapter, um, you'll notice that it is the same problem that we solved in class, that is in Blackboard, under the designation of OUY. The solution that we went through in class, and it's in Blackboard, is similar. However, in this particular problem, one is asked then for information about exergy and determining where is exergy being destroyed, and better yet, what is the exergy efficiency of the system. And so, again, all of the conditions are the same. You can refer back to OUY to see how I split up the flow rates in the high and the low pressure turbine stages. How some of the fluid went back over to the process heater, to the campus, to heat the campus buildings, and came back at a lower pressure and at a lower temperature. How it then was trapped to the condenser, all the fluid met up again, went through the isentropic pump over into the boiler, where it was raised once again up to the high energy state at state 1. This time, though, because we are going to cover exergy, we need to establish a state 0, which is the dead state. And so the dead state's going to be the atmospheric conditions at 100 kPa and 20 degrees Celsius. There's a couple of other pieces of information that are necessary because we are dealing with exergy, and that is that the heat transfer coming in to the boiler is coming in at a source temperature of 1200 Celsius. And so because we will have determined the amount of heat that is actually delivered to the fluid, we want to know, better yet, we need to know how much exergy was brought in because of that heat transfer. We also, since heat is lost in the process heater, we need to know at what temperature was it delivered to. And so in this particular case, the building is maintained at 50 degrees Celsius. And so that is the temperature that the heat transfer from that stream of extracted fluid is going to be losing its heat from. And so we have a destruction, we have an exergy component there that is transferred away from the fluid. Okay, so with that in mind, I'm going to go ahead, going to go back to the test program. And again, this is a vapor power cycle, phase change fluid. So we are going then to the test app. Again, for quickness, I'm going to go ahead and I'm going to bring in the various, the solution, and we will walk through the various states as well as the device panels, and we'll also calculate, and I'll show you how we calculate this second law efficiency. The problem says that it wants you to perform an exergy analysis. But all that really is to make sure that each of your device panels show where exergy is destroyed or where irreversibility occurs. And that will be given by the term I dot, or the flow or the exergy destruction term. So with that in mind, I'm going to again go back to my Word document, and for OXX, which is this particular problem, I'm going to bring in my states, bring in my device panels, and also bring in some user code that we'll discuss. Copy that, put that away, go into this point here, paste that into, and do a load. And so again, this brings in all of the information into the test software. So let's see what it brought in. Okay, in the state panel, you'll notice now we have a state 0. And our state 0 is 100 kPa and 20 degrees Celsius. Okay, our other states, the state 1 is 2.5 megapascals and 320 Celsius. And again, keep in mind that we had a flow rate, a mass flow rate at this particular case of 1 kilogram per second. We then isentropically expanded to 0.2, and that gave us our idealized maximum work or isentropic work. We then established state 3, which was the real condition of expansion, and that's where we put in the equation for the enthalpy at 3 based on the 80% first law or isentropic efficiency of the turbine stage. Then recall what we did was we then generated state 13, which had the same pressure and enthalpy, but it's where we then allocated 0.3 kilogram a second. That's what was going over to the campus building. And then we also established a state 23, same condition as 3, but the remainder of the fluid, 0.7. That then went into the second stage of the turbine and followed through the condenser. So with that in mind then, I'll go back then. So now we have state 4, which is the fluid that's coming in at state 23 is now going to expand isentropically through the second stage down to 6 kPa. And that's our isentropic work. We then establish state 5, which is then the real state. And again, an 80% efficiency. And so we determine what the enthalpy is coming out at that final state. That's what's going into the condenser. What's coming out at the condenser is at that condenser pressure of condenser pressure of 6 kPa, and it's also at saturated liquid condition. So that's coming out of the condenser, and we know that state 9 has come in as well as state 5 has come in and formed the full flow rate at that exit to the condenser. State 7 is the condition after the pump. And so we come out at state 6 and we go up to the high pressure. We do it isentropically because the pump is considered to be isentropic. It's a small amount of work to begin with. And then we look over coming out of the process heater was at a slightly lower pressure than the extraction pressure, 0.1 megapascal, at a lower temperature, 60 degrees Celsius. And again, the mass flow rate was the mass flow rate at state 13, which is 0.3 kilograms per second. So that's what's coming out of the process heater from the campus buildings. And then finally, we have one more state, and that is the state after we trapped the fluid back to the condensation pressure at P4, and we said that the enthalpy was equal to H8. So it's a constant enthalpy process. So with that in mind, then we have all of our states. We can then, if we wanted to, we could see where all the states were on the TS diagram, and you could see the two expansion output conditions and everything else. Our device panels then, our first device panel, as we covered last time, was a multi type of device with mixing, where we brought in the original state 1 and we took away the state 1-3. It has conditions, and then we also took away state 5. And so on the output here, we have the 2 states that represents the full fluid going through. State 1 is the 1 kilogram per second. State 1-3 is the 0.3. State 5 is the 0.7. And so we can actually have the 2-stage turbine looking like this. We say that there's no heat transfer. And so it calculates the work that's generated by the 2 stages, keeping in mind that there's some different flow rates, but it takes that into account. Now, what's also in here is we then see, because of the non-isentropic irreversible type of expansion, we see that there was a destruction of exergy. There was some irreversibility. And so this term right here, 142, is how much irreversibility occurred. This is the work that we got out. This is the irreversibility. If we would have been able to have that, we would have had this reversible work. And so this plus this equals that. And that also is the change in the psi. That's the flowing exergy. So that's our device panel. And this piece of information is necessary because we want to know how much destruction of exergy that we have. Okay, so our next device panel was from 13 to 8. That's the campus building. And the campus building, it allowed 719 of heat to be removed. The temperature that it was removed was equal to 50 degrees Celsius. That was given in the problem. And so in this particular case, what we see happening is that there is some irreversibility that occurs. Okay, we have a couple of terms here. We have this term, which is the change in the psi function between the 2 fluids. And we also have this term here, which was how much exergy is extracted when this amount of heat is taken away at this temperature with respect to the dead state. And so that number right here added to this number then gives us how much irreversibility occurs in that process heater that is the campus heater. State 3 then is the condenser. And what we said in the condenser is state 5 and state 9 come together. That's the full amount of fluid. It comes out at state 6, no work being done, and this is the amount of heat transfer that occurs. And again, we have a change in the flow exergy as we go from the higher energy, the higher exergy conditions down to a lower amount. And so we have some loss of exergy there. So that's one can think of that as being just thrown away in the cooling water. And then we have our state 4, our device 4, which is 6 to 7. That's the pump. The pump has no heat transfer. It was isentropic. And because it's isentropic, there is no irreversibility associated with it. And all of the work, which is negative, represents the change in the psi, the flow exergy of the fluid. Okay, so all of it came out in the form of work. And then finally, we have our boiler. And in the boiler, the energy balance tells us that 2,901 kilowatts of heat has to be brought in. That's at state 7 to state 1. The temperature that it's brought in is 1200 Celsius, given in the problem. which is 1473 Kelvin. And so those two numbers then show us that here is how much exergy is actually brought in due to that heat transfer. And so 2324, and that number is given by this expression right here. This is the 29, this is the 1 minus our dead state temperature, which is 293, and our boundary temperature which was 1473. And so this calculation then is how much exergy we brought into the system through the heat transfer. And then we can also talk about, the flow of exergy, how much is actually picked up, of the system. So if we calculate how much psi, how much flow exergy went in as opposed to inlet and minus outlet, we get this number here. So that is then this term here. So if I was calculating the psi inlet minus the psi exit is much higher. And so this number here is how much we added to the system. Now, what you see right away is that this is what was brought in by heat transfer. This is what actually was picked up by the fluid. And so the difference between these two is the irreversibility associated with that boiler. And so again, that's a big number. Okay, we lose a lot of exergy due to that heat transfer. Okay, so we now have all of the device panels set up. We can look at the cycle panel. And in the cycle panel, we see all of the terms that we had calculated before. We have the two works. This is the turbine work. This is the pump work. This is the net work. We have the heat transfer that was brought in by the boiler. The heat transfer that, again, this term here is the two heat transfers that leave the system. One which is leaving at the condenser, and the other one which is actually being delivered to the campus buildings. And so we recognize that part of this is associated with the first law efficiency. And so that term right there is somewhat small, because only in problem OUY did we actually determine the actual cogeneration of first law efficiency. But as we look down through here, what we then see is we see that this was our net work, okay, the net work that we got out of the system. And this is how much irreversibility was destroyed, or how much irreversibility we had in the system. And we can go back and we can look at all of those values. Okay, we lost some in the turbines. We lost a whole bunch in the boiler. Okay, so this is all that we lost. Now, if we could have kept that, then our reversible work would have been this value. That's the useful work we did get out of the system. If I could add that to that, I would then get a much larger value for the reversible work of the system. And so this reversible work then is the denominator of our second law efficiency. And what's our numerator? Our numerator is this value here. And so 683 divided by this then is the second law efficiency associated with this vapor power system. Now, in the same fashion that second law efficiency for this cogeneration plant should include something to do with the campus heating, we would have to define a little bit better with this second law efficiency. But based on just this power cycle, we see that the second law efficiency, or the exergy efficiency, is about 30%. Now in our I/O panel, all of the states and all the device panels have been identified. And in addition, last time I calculated the efficiency, the first law efficiency, by taking into account the net work, which were these two terms, the turbine minus the pump. I then also added the heat delivered to the campus as my denominator, divided by the heat that was delivered to the boiler, and that's how we calculated the efficiency. And when we did that before, what we found was our efficiency, our first law efficiency, was about 48%. Now, in calculating a second law efficiency, all that I did was I printed out the net work, which was 683, and then I included this reversible work that included the network, useful network, plus the irreversibility, and I took that as a ratio, and I see I get 30%. But once again, one would need to go back and look at the fact that some exergy was delivered, to the campus. And so that number would be higher if we made sure that we took that in account. If I'd gone back to that device panel for that 13 to 8, one should in that particular problem add an additional exergy that was delivered to the building. Okay. And so we would have put that in our numerator, and that would then cause us to have a little bit higher first law efficiency. But bottom line is the second law efficiency. Bottom line is, though, in calculating the second law efficiency, we identify these places where exergy, which was real difficult to deliver into the system, and we had a lot of losses associated with that. Those are the things that we would like to try to minimize in order to improve our exergy delivery system. And with that, that's the end of the fourth problem. Again, very much like the OUY, but in this case, talking about some exergy. I turned on the recorder again because after saying what I just said, I want to backtrack. Okay, when I mentioned that there was some exergy that was delivered to the campus buildings, and it was this amount here, that's already been taken into account because when you look at this term, this is what appears to have been lost with respect to the exergy. And but what has happened is they've modified the destruction term to account for this delivery. And so this destruction term is smaller than what it should be. So if we determine then the overall destruction included this term instead of this term 2, it would have been a little bit bigger. So it's already been calculated, and the 30% second law efficiency is appropriate, accounting for a little bit of exergy that was delivered to the campus space. But because it was done at such a low temperature, it really wasn't a whole lot of exergy that was lost.